Hello, good afternoon.
Hello, Professor.
Hello, welcome back. I hope you should see the desktop and should be hearing me by now. Does everything seem okay?
Yes, everything
Okay,
is fine.
all right. All right, so we're going to continue with language 8. Okay, let me download it. What am I doing now? Language 8 is kind of tricky. It actually brings up a profound idea in programming that you've probably not seen before because it's not really there in C or C++ or Java. It's in Python and JavaScript, but doesn't get used all that much. It's something called closures. Okay, see, we're going to talk about something called a closure, and they exist in JavaScript, but a lot of people aren't really sure. A lot of JavaScript programmers never quite really understand what they are. And here's closure. There's a general page about closures. They come out of languages like Lisp, and they come out of functional programming languages. Okay, and they become really important. The idea of a closure has become very, very, very important in modern programming. When I've said many times that languages like Java and C++ are becoming more and more like functional programming. And in a big way, this is the thing that getting closures in Java and C++ was a big step towards making them more like functional programming languages. So what we want to do is explain. Now, closure is considered a lot of people think of it as a really complicated idea. Okay, so it's not an easy thing to understand. It's going to take a little while to build up to it. So we're going to approach closures step by step using language 8. The biggest difference between language 7 and language 8 is that language 8 has closures. See, if I like last time before spring break, we were comparing the grammars of languages 7 and 8. Yeah, and if you look if you let me extract this. If you Let me clean up a little. What we were doing last time was we were comparing the grammars for these two languages. So here's the grammar for language 8, and here's the grammar for language 7. Okay, and what we emphasized last time was that there's more or less just one change, and the change is that lambda became an expression. See here, lambda in language 7, lambda only exists as part of function declarations. And function declarations are not expressions. They appear in a prog statement at the top level. There's a lot of people refer to this as being at the top level. You can a program is a bunch of function declarations followed by an expression. Now, if you think about a C program is made up of a bunch of function definitions followed by the main function. So if you can think of it, this is kind of C-like, a bunch of function definitions, and you can think of these as function definitions and variable definitions, function definitions and variable definitions, a bunch of them, followed by the main method. Okay, that's what language 7 is. It's very much like the C language. So functions have to be at the top level. Functions cannot be inside functions, and functions cannot be inside expressions. Over here, lambda exists by itself as an expression. So lambda is now like the number 5 or the Boolean true. you can just have a lambda expression all by itself. Okay. And then you can still define a function using a lambda expression, but notice now that function is a expression too. Okay. Okay. And you could even use a variable declaration. See, like here, you can say variable is expression. So instead of saying var x equals 5, now you can say var x equals lambda. Okay. So now you can do something like this. You could have var x equal, well, it would in this thing it would be var x. Normally you would say something like var x equals 5. Okay, 5 is the value, but now lambda can be the value. It could be a lambda that takes in a number w and multiplies that number by itself. So now x is a name for the squaring function. Okay, what I've written here is that x is a variable. It represents something. What it represents is a lambda expression. It's the lambda expression that takes in a number and squares it. So x is the squaring function. If you wanted to, you could give it the name SQ and it'd be a little bit easier to read. There is the squaring function. Okay, but the thing is that just like before, you could say var x5 or var x true. X had a integer value. X had a Boolean value. Now x has a lambda value. Okay, so you couldn't do this in language 8, but you can do this in language 7, but you can do this in language 8 because lambda is an expression. Okay, so that's the only, if you look at this, the grammar, that'll be the only difference you'll find. Okay, everything else is going to be the same. Apply is going to be the same as it was before. Okay, but the only difference is that apply, see over here, there is a tiny difference. Apply applies a function to an expression. So apply calls a function. But here, the function had to be declared at the top level. Okay, here, apply applies a function to an expression, but here you could apply the function directly. You in this language, you could put the lambda expression right there. Okay, you could apply what we call an anonymous function. So so now you can do something like apply. Normally you would apply f to x, or say call f with the parameter 5. Okay, but now we can say apply. Well, instead of writing a name for a function, I'll say, oh, I want the function that takes in a variable. Well, here's the function. It takes in a parameter. I'll call it, say, w, and it'll add it to itself. So it's really function 2x. Okay, and apply it to 5. Okay, you can't do this in language 7. You can't have a lambda just sitting there by itself. Okay, all right. But in language 8, you have what we sometimes refer to as anonymous lambda expressions. I can just apply the doubling function to 5, and this will evaluate to the number 10. Okay, yeah. Here you had to go look up what f was. You'd go look up f at the top level, see how f was defined, and you're applying f. Okay, so in language 8, you can do direct things like this. Okay, all right. Now another consequence of having lambdas being able to appear anywhere is you can do something like this. Okay, you could have a function f that is a lambda. So far, this is just like looks just like language 7. Function f lambda x. Okay. Now, what's the function going to do? Okay. Here's a function that squares x. okay? There's a function that doubles x, okay? Now, notice it's returning the result of adding x to x. Now, here's something real weird. Here's a function that returns a function. Okay, let's see. Okay, probably should write these. So, function f lambda x. Okay, here's the simple case. The function takes the product of x with itself. Okay. Here's another simple case. The function takes the sum of x with itself. Here's another simple case. The function applies some other function g to x. So f of x just is apply g to x. Okay. So this is all, this would still be language 7. Okay. That's a language 7 or 8 example. That's language 7 or 8. This one's language 7 or 8. This one is still language 7 or 8. Okay, you can do this in either language 7 or 8, but this one is language 8 only. Okay, what this one's a little bit different. Okay, the function f is a lambda. It takes in one variable, and then what does it give us back? Here it gave us back x squared. Here it gave us back 2x. Here it gave us back g of x. Here it gives us back a function. It gives us back a function that takes in a y and adds y to x. Okay? This is called a higher order function, a function that returns a function. If you wrote it in Java-like language, it looks something like this. Something like f of x return y goes to x, y plus x. Okay, something like this. You got a function that takes in x, but what it returns is another function, a function from y to x. So you do something like this. What's f of 5? Okay, f of 5 gives you back something, but what it gives you back is something you'd call g, because then you can do g of 6. Or if you want, you can do it this way, f of 5 of 6. Plug 5 into f, you get back the function that adds 5 to something. So see, this is the function that this function here can be thought of as the function that adds x. So this is a function whose job is to add whatever x is. Okay. So here I call f with 5 and I get back g. G is the function that adds 5 to whatever its input is. So this would give me out 11. And again, and this one also would give me out 11. Because after I call f, I get back a function, so I can call it with g. Here, I call f and I give a name to the thing I get back, and then here I call that thing. Okay. You can't do this is all language 8. You can't do this in you can do this in JavaScript, but you can't do it in Java. You can't do it in C++. You can't do it in C. Okay. You can't have there's something odd going on here that you can't do this you can't do it in C, C++, or Java. You can do it in Python, you can do it in JavaScript, and we'll look at some examples. Okay. And this is because of, let's save this. It's because we're making use of the fact that lambda can basically appear anywhere. Since lambda is an expression, lambda can appear anywhere. And what's really interesting, and this is what's going to bring up closures, is when lambda is the return value of a function. That's kind of the most important case. Okay. Now, let me show you a less important case. Here's another odd use of lambda. Here's a function f that takes in a parameter g. We'll see. Well, function f is a lambda. Let's see, what do I want to do? And it's going to take in two parameters, a g and an x. And what's it going to do? It's going to apply, okay, it's going to add x to the apply of g to x. Okay. This can be done in language. This is a language 7 or this is language 7 or 8. I'll write this in here's what this looks like in more Java-like notation. I've got a function f that takes in an x and a g. Okay, and what does the function do? The function returns x plus g of x. If you write it like this, it doesn't look that weird. Okay, so now this is another kind of higher order function. It takes a function as a parameter, and then the function is called inside here. Now you can do this in C. You can do this. This is another example of a higher order function. The function has a function parameter. Okay, this was a higher order function. This is a higher order function. And what it does is it has a function return value. This is a higher order function. But it has a function input parameter. That's a higher order function, but not as sophisticated as this one is here. Okay. Now, I can do this in language 7 or 8. Now watch, here's something I can do in language 8 that I can't do in language 7. Well, let's see. Here's an example of using it. Okay. So function squaring. The squaring function is a lambda x times x. There's the squaring function. Okay. Now apply f to 5 and the squaring function. Okay. Okay. So you're going to call f with, this is the parameter 5, and this is the squaring function. So it's going to be 5 plus 5 squared. So give you back 30. Okay. This is still language. You can do this in language 7 or 8. Yeah. This is language 7 or 8. Now here's something you can only do in language 8. Apply f to the number 5 and the anonymous lambda expression that takes in a y and doubles it. Okay. I'm calling, now I'm using the fact that I can put a lambda anywhere. So here, there's the lambda expression. There's the anonymous function that's the parameter to f. So now I'm calling f, x is 5, and g is this lambda expression that has no name, anonymous lambda expression. Okay, right? So in language 8, I can put lambdas anywhere I want. So I'm just showing you examples of putting lambdas anywhere I want. For example, here I called an anonymous lambda expression. Yeah, I just, yeah. Oh, so this one's lambda. This one's language 8 only. Because I applied a anonymous function. This one would be language 7 or 8. Okay, because you're calling a function that's been given a name. Okay, so you're applying a function that's got a name. So that's language, you can do that in language 7 or 8. But here I'm applying a function that has no name, a lambda expression. That's language 8. Okay. Here I'm defining a function that returns a lambda expression. Okay. That was this higher order function with a function return value. Okay. Then now I have a higher order function with a function input parameter. I could call the function with a named parameter. See, there's the function parameter's got a name. So this is language 7 or 8, but this is the tricky one. This is the new thing. I'm calling my higher order function and passing it the lambda expression directly. Okay. People do this all the time now in Java. This has become a very common thing to do in Java. Call a function and pass it a lambda expression. Okay. This is very common now in Java. This one's I should put the order of these in the other way. This is the more complicated case here. Function return value is the really complicated case. Okay, function parameter is kind of the common case in languages like C and C++. It's where languages like C and C++ make use of anonymous lambda expressions, but in kind of an easy way to use them as function parameters. We want to really, where closures come in is this case here, function return value. Okay. So we have two kinds of higher order functions, higher order functions with function parameters and higher order function with function return values. Both of them make use of lambda expressions, but one of them makes use of closures. Okay. So you can kind of summarize that by like two kinds of higher order functions. The easy case, function parameters, and then the harder case, function return values. Okay. So what's a first order function is a function that takes in primitive variables, ints, doubles, booleans, and returns primitives, okay? And also objects. So it'd be a function that takes in values. Well, that's a function that takes in anything that's but a function, not a function. Okay, so a first order function, its inputs and its outputs are anything but functions. So the input could be numbers, booleans, objects, uh, trees, lists, but the input can't be another function. Like a higher order function has either a function as an input or function as a return value. Function as an input, function as output. This is the easy case. This is the harder case. Now, both of these can use lambda expressions. Both kinds of higher order functions can use but in language 8. Okay. In language 7, you can still, okay, language 7, should be careful here. Language 7 allows this kind of higher order function. And this kind of higher order function is only in language 8. Okay, that's an important distinction. Function parameters, there was nothing that stopped us in language 7 from, and the C language allows this. You can have a function parameter. You can have a function that accepts a function as a parameter. That's language 7 or 8, okay? But function return values are in language 8. Now, if you look at the grammar, you can see why that is, okay? Let's go, here's the grammar for language 7. When you declare a function, you define it to be a lambda, okay? The lambda expression takes in a bunch of names and then does something with those names. Okay, there's nothing to stop one of these names from being the name of a function. And then in here, you could call that function. Okay, there's nothing in this grammar because see, this is an arbitrary expression. An arbitrary expression can be an apply. So inside here could be an apply, and you could be applying a variable name that came from this list that's actually a function. Okay, it had to be a global function. But there's nothing in this language to stop you from having a lambda where one of the parameters is a function. Okay, now, but look at the return value. There's the return value of the lambda. The return value can be the result of one of these. So you could return a Boolean, an integer. Okay, now, actually, oh, I take it back, no, you can return a function because if one of these input variables is the name of a function, you could return that variable as a function, okay? You could return, so you can actually, I was wrong, you can do this in language 7 or 8, okay? Okay, but you still can't, but you can't do this in language 7. See, the key is that, well, the key is you can't define the function locally. See here, I'm returning a function that's defined inside here, okay? So a higher order function either takes a function as a parameter or a function as a return value. What you can't do in language 7 that you can do in language 8 is define the function inside The return function can be defined inside of the function. That's something that's actually, I forgot, that's called a nested function. Okay. So right here, I have a higher, this is a nested function return value. That's what I forgot to mention there. That's actually, because see that this is defining the function. So that's what we mean by nested. Nested functions when you define a function inside of a function. Okay. So this is a higher order function, but it's returning a nested function return value. Okay. So let me show you a higher order function that doesn't use a nested function. Okay. So here's kind of a dumb example, but you can do this. We did it earlier. Okay, so there, sorry, fun h is a lambda that takes in two parameters, and what it does is, okay, it'll take in three parameters, f, g, and x. Okay, and then it'll say if x is less than 0, return f, otherwise return g. So it chooses between the two functions. So h takes in functions in and returns a function out. So h is a higher order function, f is a function in, g is a function in, and then it's going to return either f or g. So it's a higher order function with a function parameter and a function return value. But notice that there's nothing in here that defines the return function. The return function just is one of these two. So that's, you can do this in language 7 or 8. Okay. This is a function return value, but not an interesting kind of one. I mean, it's useful. Actually, this is kind of useful, but it's not the complicated case. The complicated case is this one, a nested function return value. Now, you can do this in language 8, because in language 8, in the body of a function can be a lambda expression. So that means that you could define a new function inside of a function. Okay, so in the body of a lambda expression, this expression here can have lambda expressions buried in it. So a lambda expression can have lambda expressions inside of it. Okay, so there's the circular nested function thing that language 8 gives you. And that's what's really going to be interesting. That's what really makes things complicated. A lambda expression has a return value that's expression, but expression can be another lambda expression. So the function can return a new function. That's what we did here. The function is returning, essentially, this is another lambda expression. So the function is building a new function in here. In language 7, the body of a lambda expression can't have a lambda expression in it, because the body of a lambda expression is this. And none of these are lambda expressions. Now, again, I made a mistake. You could return a function, because the body of this guy could be returning a variable which names some global function. So you could have a lambda that returns a function, but it can't define the function inside of itself. It has to return some function that's defined outside of itself. Okay, so you can only do this little trick here of a function that chooses a function. So this is a higher order function that takes in two functions as parameters, and it returns a function, but it's just returning one of the choices. So it's not especially deep or interesting higher order function. Okay, this is a more complicated one up here. This is a higher order function that's returning a function, but it builds the function internally. It's got a lambda expression inside of a lambda expression. Okay, so what we need to do is make sense of all this. I mean, this is confusing. This stuff has a reputation of being really tricky. I've been teaching this stuff for years, and what I keep trying to find is a good linear, logical way to present these ideas. And I've never been able to come up with one. I've never seen anybody do it. Uh, it's a bunch of ideas that are tightly interwound. And what we're going to do is we keep defining all the words, and eventually you have to kind of put them in. It's a circuit. It's kind of like a big circular argument, and you have to, at some point, you have to see how it kind of fits together. We're going to define all the words, and we'll keep coming back to it, but we'll see that eventually they all just kind of fit together. But there's no real easy linear way to explain it. So words are things like, what's a higher order function? Okay. And what's a function parameter? What's a function return value? What do we mean by a lambda expression? What do we mean by a nested function? Okay. Okay. So higher order functions, function parameters, function return values, lambda expressions, nested functions, closures. These are the ideas, all the ingredients yeah. And what we want to do is kind of like, and all of this is coming out of one real, yeah, all this comes out of just one stupid little change. Move lambda to here. Move lambda to here. And that tiny little change in the grammar brings up all these ideas. Okay. Over here, you do have higher order functions. You do have lambda expressions, but not anonymous lambda expressions. And you don't have nested lambda expressions. Okay. Over here, you have anonymous lambdas and you have nested lambdas. Okay. So over here, there's two new things. And oh, you see, it's in the title here. See, a language with first class nested anonymous functions. That's really the two new things that are coming up here: nested and anonymous. Okay. Over here, over here you have higher order functions, and over here you have higher order functions. We didn't put much emphasis on higher order functions over here. We did a little bit with them earlier, but they haven't yet quite seen their real power. The real power of higher order functions comes over here when you start doing nested ones. Okay. All right. So when you move lambda to here, you get nested anonymous functions, and then you need closures. Okay. So you move lambda to here, and you get two new ideas, and you need a closure. Without the closure, this won't work. Okay. We'll see in a little bit that there's something's really changed in this language here. It took years for computer scientists to develop language 8. Language 8's the reason. Right now, it makes this is kind of deceptively simple, even though it seems complicated. It actually is appearing more simple than it really is. It took many years, like 20 years, for computer scientists to figure this stuff out. They started. Lisp was invented in the 1950s. It wasn't until the late 70s, early 80s that people really understood what Lisp was doing. The language existed for a long time and was in use. And it wasn't until somebody invented Scheme and some other things in the 70s and 80s that they really started understanding exactly what was going on. And then they realized how powerful Lisp was. Lisp went from being kind of a kind of oddball language to actually being one of the key languages in computer science. Except that by then people stopped calling it Lisp. They redefined the language and gave it other names. So they used names like Scheme and ML and eventually Haskell. Okay, but they started really realizing how profound these ideas were. What was happening when you move lambda over to here. When you move lambda from here to here, what that really did to you. Okay. So, and here it's just one little change in the grammar. It'll be a medium-sized change in our interpreter, but there's one big change from language 7 to language 8 that we're going to we'll go back to it later, and that's called garbage collection. Okay. We can write language 8 in Java because it's a garbage collected language. Language 8 is very hard to write in C++. If this was a course that used C++ as the programming language, we would have a hard time implementing language 8. Very hard time. The interpreter for language 8 would be very difficult because what we would have to do is we would have to write a garbage collector. To implement language 8, it's not going to be clear to us in this transition from 7 to 8, but language 8 requires a garbage collector. Language 7 doesn't. We can implement language 7 in C++ without any trouble. It'd be real easy to do it. Language 8 to implement in C++ would be very difficult. You'd have to essentially write a small garbage collector. Okay? Or there's some other things you could do, but they'd be equally hard. You'd either write your own garbage collector, or you'd have to do some other tricks that are equally hard to get language 8 to work. Okay? And this is one of the reasons why this took so many years to figure out, was because in the 60s and 70s, no languages had garbage collectors, or garbage collectors weren't very common. And if you're writing your code in assembly language, or you're writing it in C, or you're writing your code in C++, when you try to write an interpreter for language 8, it becomes hard. And you just, it makes you think that there's something wrong here, because it's just so much harder to write language 8 than language 7. But then when Java came around and gave you a garbage collector for free, this is actually one of the reasons why they put in a garbage collector, it lets you write much more powerful things easily. So like an interpreter for language 8 becomes easy in Java. Okay, all of a sudden we can write an interpreter for language 8 without much effort. Okay, because Java gives us the garbage collector. And that's a subtle point that even a lot of the textbooks kind of gloss over. The transition from language 7 to language 8 requires a garbage collector in the background. Now, actually, you can, if you write language 8 in C++, more or less the way this Java one is written, you can do it, but what'll happen is you'll have a memory leak. And if you run your program for very long, eventually your C++ interpreter will run out of memory. So you could write an interpreter for language 8 in C++ without a garbage collector, but after your program runs for 15, 20 minutes, it will have used up all the memory and it'll crash. Okay, because it won't have a garbage collector. So, and we'll see what memory gets, there'll be, well, as we go deeper into this, we'll see what is it that garbage collector is collecting for us. We'll see what it is the closures, these things we're going to call closures. They're the things that are being garbage collected. Okay, so Java garbage collects the closures. Okay, if you don't garbage collect the closures, they accumulate in memory, and then your program will eventually crash. Okay. All right, so there's a whole bunch of ideas here. Lambda expressions, higher order functions, nested functions, closures, garbage collection, all intertwined. Okay, so all these ideas are intertwined. Let me see if I can. Lambda expressions, higher order functions, nested functions, and garbage collection. Now let's see. Higher order functions are in even language 7. That's an interesting idea, but it's not a deep idea. Okay, lambda expressions are also in language 7, but not anonymous ones. So there's lambda expressions, and then what's a little bit more interesting is anonymous. Okay, so this is language 7, this is language 7, then this is starting with language 8. Anonymous lambda expressions, nested, well, I'll say nested lambda expressions, and garbage collection. Oh, and then, well, closures and garbage collection. Okay, so these two ideas, they're not profound. They're in Java, they're in C++, they're in language 7. Okay, they're in language 7, but people tend not to think of them too much. the higher order function means a function that takes the parameters, an input parameter is a function or output parameter is a function. A lambda expression is just the body of a function. That's all it really is. So that's what language 7 does. In language 7, the lambda expression is just the body of a function. Okay, that's not very interesting. But then anonymous lambda expressions let you take the body of a function and use them by themselves. So you can strip away the name and just use the body of the function wherever you want. And then you can start nesting lambda expressions inside of lambda expressions. Then you need closures, and then you need a garbage collector. Okay, so there's a big jump from here, these two ideas, to these ideas here. Okay, so language 7 has these, but then language 8 really introduces these. Okay, so that's another way of organizing the ideas. It's a bunch of words, okay, bunch of ideas, bunch of words, that are kind of intertwined. Okay, I mean, these come first, so you can, higher order functions and lambda expressions, you can define them in terms of language 7, but they don't seem very interesting. In language 7, if you talk about a lambda expression, you're just talking about the body of a function. Every function has to have a body, so it hardly seems worth giving a name to it. It's just the body of a function. That's what we mean by a lambda expression. And higher order functions, you can do some interesting things with higher order functions. Sorting is an example of sorting algorithms usually take a comparator function as input. So you can do some interesting things with higher order functions, but not a huge amount. Okay. But then when language 8 comes along and you move lambda over to here, so you move lambda into expression, all of a sudden now you have anonymous lambda expressions, nested lambda expressions, closures, and garbage collection. Okay. And so now you have these 4 ideas here. Okay. All right. So now let's look at this from another point of view. Okay. So what I'm doing here is introducing to you the ideas. Okay. So these are the ideas here are the ideas that are being introduced up here. Okay. Now let's go through some of these ideas in another way. Let me show you another point of view of all this. I've got some notes. I haven't put these in the, I wrote some notes up. I haven't put them in the folder for language 8. I'll put them after class. I'll put them in the folder. Okay. Here's some ideas in an order. Okay. This is me. I told you, I'm trying to put these things in an order where it can explain them. So here is some other, here's another word, binding. Okay. Open expression, free variables, non-local references, closing, lexical scope, dynamic scope. We've talked about lexical scope and dynamic scope. So right now we're going to kind of introduce them with another set. We're going to reintroduce lexical and dynamic scope with some new terminology here. Okay. And anonymous functions. Now this is where things, everything up here we've talked about off and on. Okay. So we're going to reintroduce them and be more careful about them. And then here's where things get interesting when we talk about nested functions. Okay. All right. So, okay, let's start with here. What's a binding? Okay. Okay. Binding is an idea. Bindings are what our environments do. Okay. Binding is what an environment does. A binding is associating a variable to its value. Okay. So actually, there's a couple ways of thinking about what the word binding means. Okay, here, look at these examples. There's a declaration of a variable. Okay, down here, I declare another variable and I make use of x. Well, you go up here and that's what the x is. Okay, now down here, see, now I start another scope. See, there's a brace, so that starts a block. Okay, here's an x. And then here's another variable declaration of x. So notice I've got 2 x's. The word binding means, who do I bind that x to? Should I bind it to him or should I bind it to this? So which declaration should this x be bound to? Okay. Now, in Java and in C++ and in Python, you'd bind it to the variable that way. But we've mentioned before that in JavaScript, it's actually bound to that guy because they're in the same block. In JavaScript, you bind a variable to its declaration in that block, even if the declaration comes later. So in JavaScript, this X is bound to that X, but it doesn't have a value yet. So when you print X, it'll print the word undefined. That X will be bound to that X. But in Java, C++, and Python, it'll be bound to that X. Okay. So binding means associating a variable use to a variable declaration. This is we call this a use or a reference to a variable, and we need to bind it to a declaration of the variable. Okay, there are all kinds of different bindings. There's lexical scope bindings and dynamic scope bindings. Okay, that's back to this idea of lexical scope and dynamic scope. One way to think about the words lexical scope and dynamic scope is about bindings. Okay, now both of these are, this is a lexical binding and this is a lexical binding. Neither one of those is a dynamic binding. Those are both lexical bindings. In the case of Java, you go to the previous declaration. In the case of JavaScript, you use the declaration that's in the block you're currently in. So we're currently in that block, so we use the declaration that's in that block. Okay. Okay. In JavaScript, if we wrote the var here, then this would also go like that. Okay. But that's because it's in the same block. So in JavaScript, this would go to this one, but also in Java and also in C and C++. Okay. But JavaScript doesn't say use the previous declaration. It says use the declarations in the current block. So in the current block, if it's like this, JavaScript goes, oh, this is what's in the current block. That's a lexical scope, but a weird one. Okay. Let's see. If I wanted to make a dynamic scope, let's see. Can I make this one have dynamic scope? To get examples of dynamic scope, you usually have to have function calls. Dynamic scope always said use the X that's most recently declared, the most recently declared in time. Okay, if this was dynamic scope, it will still go to this one. Let's see. I'm trying to remember how to make, if you can clearly show, what's the easiest way to show a difference in dynamic scope? Now I think you have to have some kind of function involved. You know, you can't do if you're just going to use blocks, it's hard to explain dynamic scope. Dynamic scope needs to have a function involved. Now we'll leave it here. I'll think about that after class. But the word binding means associate a variable use to a variable declaration. Okay. Okay. There are both static bindings and dynamic bindings, but even static bindings come in different flavors. This is one kind of static binding, and this is another kind of static binding. Static binding means you can figure it out by looking at the text on the page. Dynamic binding means you have to run the program. Yeah, if I'm using in a dynamically scoped program, to know what X you're going to print, you have to run the program. Now, in this case, it's such a simple program, there's no question. But in a dynamically scoped or dynamically binding, you have to run the program to see which X that's bound to. In statically scoped, you can just look at the code and tell. Okay, this is one kind of looking at the code and figuring out what it binds to. And this is another looking at the code and figuring out what it binds to. Those are both lexical static scope, but different kinds of lexical scope. Okay. Now, here's an important idea, open expressions, okay? Or another, there's a bunch of different words here, open expressions, free variables, or non-local references, okay? If you give me an expression where there's no binding for one of the variables, that's called an open expression. And the variable without a binding is called a free variable. So like, look at this. Look at that expression. By itself, it has no declarations, so it's got 3 free variables. Here's another expression. There's not, just by itself, it's got 1 free variable. This one's got 2 free variables. Now look at this one. This is a declaration. It declares a parameter variable. You know, if you think about it, if you think of it in terms of Java, you'd write something like f int x, but that's a declaration. Okay, so this x is bound to that declaration, but this guy's the free variable. Okay, so function parameters are examples of declarations. Okay, so a binding can be to a function parameter. So in this expression, there's 1 bound variable and 1 free variable. In this expression, there's 1 bound variable and 2 free variables. Okay, and this one here is just this example here written in Java notation. Okay, f takes in the parameter x, so that declares x. This x is bound to that x, and a is a free variable. Okay. All right. So this is an idea that if I show you an expression, I can just I'm here. I'm pulling an expression out of a program, and I'm just giving you an expression saying what are the free variables and what are the bound variables in that expression. Okay. So anything that's not declared is a free variable. Okay. So now we have the idea of closing an open expression. To close an open expression it's a form of binding. So this is back to the idea of binding. You close an open expression by finding a declaration. You bind the free variables to some declaration. Okay. So here's an example. Like here, there's no free variables. You have 3 variables declared here, and there's 3 variables used here. So this thing has no free variables. Everything is closed. It's a closed expression because there are no free variables. Okay. Now, here, that's an expression with a free variable x, but then here I give you a binding for it. So I say let x equal to int. Now, if I wrote this in Java, it would look like this. It would be int x equal to 2 times x minus 8. Okay. Those two now those are 2 statements, but those 2 statements are closed. There's no free variables in these 2 things together. Okay. It's more, this is using Haskell, JavaScript. JavaScript has let Haskell, ML. It's kind of a nice way to say bind x to 2 and then write down a expression that otherwise would have x as a free variable. So this has x as a free variable, and this is the binding. So this is a closed expression. Another way to say is that this thing closes off this one. This statement closes that one. You know, if you drop this one, then this one won't work unless you find some other binding for x. Okay, so x is free in this statement. This one closes that statement there. Okay, this is just another example of the same thing, just binding x to a different value. This is an example out of math notation. The set of all x such that 2x squared minus 6 equals 0. Okay, that defines a set of numbers. The set of all x's that solve this equation. Okay, notice there's no free variable here. This x, if you look at this, that's got a free variable in it. But this is saying, I want the set of all x's that make this equation true. So there's no free variables in this. This is a form of a closed expression. That comes out of math. That's something you would see maybe in a calculus book. But it's an example of a form of closing an open expression by saying, I want the set of all x that solve this equation. Okay. The equation by itself has a free variable in it. And if I just wrote that equation by itself, you don't know what I want you to do. Do I want you to solve the equation? Do I want you to plug in some number into the equation? See, this thing closes it and says, oh, I want you to solve the equation. I want you to find all the x's that make the equation true. Okay. Here's something in English that says this closing expression. See, this expression's open. It's got an undeclared variable in it, but then it says there exists an x such that 2x squared minus 8 equals 0. Notice that in that sentence, you know exactly what x that is. It's the x. It's saying there is an x such that 2x squared minus 8 equals 0. Okay. So this is not a free variable in here. It's the x I'm talking about here. It's the x that makes that equation true. It's another version of this one here. This one says, give me all the x's that make that equation true. There's two of them. And this one just says, though there is at least one x that makes that equation true. Okay. These are math English examples of closing an expression. Here's another one. This is actually a false statement. It's saying that for all x, 2x squared minus x is equal to 0. Okay, that's a false statement. But notice that this x is not free. It's this one that's saying that it's saying that you should be able to take any x and plug it into here and get a true statement. So this is a false statement because it says that for all x, blah, blah, blah. Yeah, this is a true statement. There is an x such that that's true. Okay, like here's a true statement for all x, x times x is greater than or equal to 0. Okay, that's an example of this has got a free variable in it. This closes the free variable. I'm saying for all x, that means you plug in every number in here, and it's saying that for all x, this is true. And it is true that for all x, its square is a positive number. So this is a true statement. This is a false statement, but they're both closed. Now, if I did this, that's not a closed expression. Now, this statement doesn't make any sense. For all x, x times y is greater than or equal to 0. That's not true. That's not false. It's just by itself kind of, well, it depends. If I go up here and say, let y equal 5, now this is closed and true. Okay. See, now I would be closing that expression with that one. On the other hand, if I say let x equals -5, let y equals -5, now this is closed and false. Okay. But these two together are closed. This closes off. See, now you go back. Where's y come from? Well, y is right there. Okay, so now I know where y comes from. So I use that y, but then this is a false statement. For all x, x times y is positive is not true. Okay. All right. So these are examples of like this closes what would otherwise be an open expression. Open expressions means you've got some variable that isn't defined, and you close it by giving some context that gives it a definition. That gives the free variable some definition. Okay. Okay. All right. Like here's a more Java-ish version. Okay. By itself, this thing's open because there is a there that's not bound to, see, it's not bound to that local variable. There's this x is bound to there. But if you just look at this by itself, it's open because there's no declaration of the a. But if you add this, then it's closed. So this closes that for me. This is open. This with it closes it. Okay. So it's kind of a weird idea. Something can be open and then something else can close it. Notice that it's very closely related to the idea of binding. Okay. Down here, this is an open expression, print x. Well, what x are you talking about? Well, you could bind x to this one up here. Okay, then it's closed. So binding is a form of closing something. On the other hand, you could bind x to this one down here, but that still closes it. Okay, except that it doesn't give it a value. Notice that that closes the print x, but doesn't give it a value. In JavaScript, that'll print undefined because x is closed but doesn't have a value yet. So that's why JavaScript's such a weird language. You can close an expression in JavaScript without giving the variable a value, which hardly seems to be right. That JavaScript will let you close an expression, but without giving the variable that's being closed a value. That's one of the reasons why JavaScript is like inherently a poorly defined language. It lets you do something weird where you have a binding and that closes an expression, but the expression still doesn't have a real meaning. It's going to print undefined. I mean, that's a legitimate, correct thing to do in JavaScript, print undefined, but that just seems like a really weird way to define your language, to let variables be undefined. I don't know of any other language that lets variables have a legitimate value, that the legitimate value is that the variable doesn't have a value. Yeah, that the variable is defined to be undefined. Talk about nonsense. The variable is defined to be undefined. So, but see, that's one reason why these ideas are so hard to pin down, because even like a language like JavaScript can muck it up. These ideas don't really exist in a real nice, easy to explain linear order, because if they did, you wouldn't have this craziness of JavaScript mucking it up and having a variable that's defined to be undefined. So it's a circular sea of ideas, and the designer of JavaScript, in his haste to design JavaScript, forgot to realize all the implications of what he was doing, and he kind of left this hole in the language that of the way it worked. And the language did bindings and closed expressions, but it closed them without giving them values. Okay, so it's a weird mixture of ideas that aren't real easy to pin down, and the proof that they're not easy to pin down is that pretty smart people screwed it up when they were trying. If they didn't give themselves enough time to think about this stuff, JavaScript was famously invented in just 2 or 3 weeks, and that was just not enough time to invent a language. And we're stuck with the initial bad decisions he made, because once he made those decisions and put them in print, nobody had the guts to change them. You know, nobody put their foot down and said, we're going to change the language. Even though we've been using it for a year or two now, we're going to change the language because this is just kind of dumb. Nobody was willing to do that. So it's now 30 years later, and we still have this kind of weirdness. Okay. So bindings are like closing. Binding and closing are a very similar idea. An open expression gets closed by a binding. Okay, so like here, this would be an open expression by itself. It's closed by that binding. Okay, without that binding, it would remain an open expression, and without that binding, it won't compile and it won't run. You can't actually run programs that have open expressions. All expressions that are open need to be closed by something before you can run your program. Okay, so in that sense, you wonder, why do we even talk about open expressions if programs don't have them? Programs can't have open expressions, but it's an important idea. You know, we'll see as we go along how talking about open expressions and bindings helps us understand ideas in programming. No program can have an open expression in it, because when you hit the undeclared variable, you just don't know what to do. So open expression is an idea that we can use for talking about programs, but it's not an idea that you can have in any legitimate program. Every variable must be bound for a program to actually run. Okay, right? then lexical scope and dynamic scope are two ways of doing bindings or of doing closings. Okay, we say again, lexical scope was you can look at the paper, you can look at the code on the paper and say what it's bound to. You can look on the page and say what it's bound to. Dynamic scope says you have to run the program. Like here's an example with dynamic scope. See, it takes a lot more boilerplate to give a dynamic scope example. Yeah. The key is this guy here. What does he get bound to? Okay. See, that's a free variable in that thing. So it's a free variable. It needs to be closed. Do you close it lexically or not? In this example, you could close this guy with this one or with this one. And down here, it shows you how, depending on how you run the program, sometimes this guy is closed with this one, and sometimes this one is closed with this one. That's the problem with dynamic scope. It isn't until you run the program that you could tell which declaration closes the open variable. Okay, so there's the open variable. You can see it's open because that function is open by itself. So something needs to close off that y. In a lexically scoped language, it would be this, but in a dynamically scoped language, it's whatever is the last y that was declared. It could be this one, or it could be this one. And it gives you examples down here to show you how you can get it closing either way. Okay, but notice that the idea is this is free. It needs to be closed, needs to be bound, but there's lots of ways of choosing a binding. Lexically, dynamically. Okay. All right. So those are important ideas. Again, in the history of programming languages, these ideas took years for people to. It took years for them to start pinning down the idea that we got to be really precise about what we're doing. These things weren't clear to them. So a lot of times when you learn programming, you kind of take a lot of these ideas for granted. You learn Java, so you just learn the way Java does things, and you don't realize, oh, there are other ways to do these. Oh, this thing that I automatically think Java does this one way, it really could be done a different way. Should it? Is Java doing it the right way? Is Java doing it is Java doing it the best way? Here we're trying to force ways of thinking of saying, well, okay, here's a free variable, bind it, and then figure out what's the best way to bind it. Well, what Java does, lexically scoping, is the best way to bind it. But there are other ways. Dynamic scoping was another way. Okay. Okay. So we're running out of time. On Wednesday, we'll keep talking about these ideas. Scope, binding, closing, and then we'll see how it leads to, and again, we're going to go back to lambda expressions, nested lambda expressions, and we're going to go back and we're going to see how if we, eventually all these ideas come together into a really important idea called closures, which is, the heart of functional programming. Okay, so all this messy stuff will be resolved in kind of an elegant way using closures in functional programming languages. Okay, all right, so we'll quit there. Oh, remember, you got a programming assignment. If you have any questions about the programming assignment, it doesn't use what we're talking about now. The programming assignment is definitely about only language 7. It's a language 7 programming assignment. But if you have any questions about it, we'll see. You come to office hours or send me email. Okay, because it's a very nice programming assignment. It's very much, it doesn't use anything that we're talking about in language 8. It's very much a language 7 only programming assignment, but it's a real nice one. So if you have questions about, send me email or come to office hours. Anybody got any question about what we did today? It's a mess of ideas. I admit that it's a mess of ideas, and I think what you should do is make up your own notes. Like I'll put the notes I've been putting up, but you keep track of the words we're defining. Probably the best way to do it is to think of the words we're using, like binding, closure, free, lambda expression, nested functions, and keep trying to remind yourself what those words mean. So keep a list of the words, try to remind yourself of what they mean. Try to go through them and define them yourself. And write little snippets of code that would use, like write a snippet of code with a free variable. Write a snippet of code that closes it. They're simple ideas. Okay. But eventually all these ideas will come together, but it takes a while to see how they all come together. And like I say, closures are an idea. If you Google closures, you'll find tons of pages about them. Some are right and some are wrong. It's not hard to find people writing about closures who are writing nonsense. Okay. And then there's a lot of really good stuff written about closures. I'll maybe try to find some good links to good stuff written about closures, and I'll maybe even show you some links of people writing nonsense about closures. It's a tough idea. So you'll find plenty of people who think they can explain it, but they end up explaining it really wrong. And then there's people who explain it really well too. But all the explanations of it well are hard to read. There is no easy to read good explanation of a closure because it's a tough idea. So when somebody writes a simple explanation of closure, it's almost always wrong. And when somebody writes a good explanation of closures, it's almost always complicated. It's not an easy idea. Okay, so that's what we're going to get. That's what we want to build up to, is exactly what a closure is. Okay, any question? Oh, one last thing. The word closure is such an important part of the language that somebody even came up with a joke. They named a programming language Closure. They changed the S to J, and it's a double pun. It's called Closure because closures are such a key concept in the whole programming language, and it put a J in the middle because Closure runs on the Java virtual machine. So they used J in the middle of the word as to denote, oh, we run on the Java, we're a Java virtual machine language, but we're a language based on closures. So it was like a double pun. But that's how crucial the idea is. See, oh, there's the lambda. See, there's the lambda based into the symbol for the closure language is this kind of weird thing with there's the lambda inside of it. Okay, lambda expressions, closures, they're the heart of modern programming. Closure is a real famous modern programming language. A lot of stuff gets written about Closure. Very, very famous, very popular language for experimenting with ideas. Okay, so it's considered a very elegant modern language, and it's just kind of fun that uses Closure in a pun like this to name the language. Okay, so we'll quit there, and okay, on Thursday we're just going to keep doing more of this. We're going to keep chasing our tail around these ideas: closure, lambdas, nested. Yeah, and we'll try until we can get at a good sense of what they all mean together. Okay, so I'll stop sharing. We'll meet again on Wednesday. And I'll put these notes on that I was talking about today. I'll put them up on the website so you can look at them. Okay, bye-bye.